So today we are going to talk about the aromaticity. So directly we'll solve some of the questions which asked in previous exams. So this is the one. A, B, C. So this question asked in a CSR in 2011. So they have asked which one is aromatic, which one is homoaromatic, and which one is anti-aromatic. So we know that we have 4n pi principle plus 2 pi system, which it follows this aromatic. If it is 4n pi, that is anti-aromatic. So here we have 2 pi electron system. This is aromatic, and this is a 4 pi electron system. This is anti-aromatic, and this is aromatic, and this is comes under special aromatic character, that is homoaromatic. So homoaromatic means this will follows 4n plus 2 pi system 5 rule, but the delocalization will get disturbed by the sp3 type carbon atom. So because of that reason we call it as a homoaromatic, but still it is a compared to anti and non-aromatic, it is stable. And then next question they have asked, this is the one. It's 2, 3. So they asked which one among the following is aromatic. This question asked in December 2011, and this is the June 2011. So here these hydrogens are facing opposite to each other. So because of that reason there is a steric crowding. So because of this steric crowding, this 10 aniline cannot attain the planar structure. So because it's aromatic only because this 10 pi system, this is aromatic, but still because of these two hydrogens are facing each other opposite, so it cannot attain the planarity. Because of that this is the non-planar. So non-planar means non-aromatic. Whereas if we can connect these two carbons with oxygen, sulfur, NH, Pr, etc, so then that will become aromatic, means that will become planar. So here this is the aromatic because these two carbons are connected by the oxygen atom. It can be any heteroatom, then it will be aromatic, and we know that this is a naphthalene, this is also aromatic. And next question we have, so this question asked December 2013. So the question is, among the following A, B, C, D, among the following, the lowest energy barrier for cis and trans isomerization is. Just remember that the compound which shows a aromatic character, like in among this one, if you take this compound, so in this case, so this is the aromatic. Okay, so this kind of compounds where we are getting aromaticity by this way. So here aromaticity is directly proportional to dipole moment, and then directly proportional to polarity, and then these compounds are having a less energy barrier, and then last one is it's inversely proportional to the hydration energy. Okay, so hydration energy is inversely proportional to the stability, right? I think, if I'm not wrong. Sorry, not hydration, heat of hydrogenation. Heat of hydrogenation. So you just remember these 4 points. So this question also frame like which one is having more dipole moment. So this is the answer. Which one is having more polarity? This is the only answer. Which one is having less energy barrier for cis and trans? This is the only answer. And if they ask which one is having least heat of hydrogenation, this is the answer. And then we have 4 compounds here. A, B, C, D. So the question is, which one is anti-aromatic? So for anti-aromatic, we have to see the 4n pi system. Okay, so here we have 4 pi electrons. So this is a 4n pi system. This is anti-aromatic, and this compound is aromatic. Just remember that. So when we have a carbonyl compound like this, here this will be positive charge and this will be negative charge. Never we cannot consider this double bond in the like part of aromaticity, because this exists like this. Okay, because of that reason, this is aromatic, and this is also aromatic, this is also aromatic, but this is a anti-aromatic. Then we have one second compound is this. So the question is here, among the following is A, B, C, D. Among the following, which gives the warming precipitate on warming with the aqueous AgNO3. Okay, that means precipitate forming means we have to generate the AgCl, sorry, AgBr. Okay, so For that we know that this is Ag plus, Br minus has to come from here. If it become Br minus, it will become like this, and then it is like this. Sorry, Br minus, right? This plus, plus, this is plus, and here we are getting a tropylium cation, right? So tropylium cation is the aromatic, so the correct answer is C. This is first one plus 2K plus H2 SO4 So these four questions they have asked, sorry, one question only. They have given four compounds in a net 2016 exam. So they asked us to find which one is aromatic and which one is not aromatic. So just remember here in this case, so when you are treating with metal, so this will get converted to 2K plus. That means two electrons are adding to this ring. So here -2. Then so this one will get converted to 2H plus plus SO4 -2, and these two will form a addition reaction here. Like this, and here this is a electrocyclic reaction. Okay, so now these two form a bond, and these two form a bond, and here to the total system 2 electrons are adding. So how many metals they give, that many electrons will get add. Here -2. So now we'll see here in the options we have four options. We have aromatic, anti-aromatic, non-aromatic, homoaromatic. Okay, so this will comes under the homoaromatic, and this will comes under non-aromatic because it's not a planar. And if you see this one, count the number of pi electrons: 1 2 3 4 5 6 7 14 plus 16. 16 electron means this is a anti-aromatic, and this one will be aromatic. And next important compound is that azulene. So azulene means one 7-member ring and one 5-member ring joined together. So this will not exist like this. Always it exists in the ionic form, so that it get a aromaticity. Okay, always it exists in this form. So that's why uh, there are in the gate exam in 2000 and 2004, 2008, 2009, four times asked question on the aniline. So in the first question, like in 2000, what they ask, the following hydrocarbon has dipole moment of 0.8 d because of, so the options what they have given, it exists in ionic form in which both the rings exhibit aromaticity. So that is the correct answer. So because of the it's existing ionic form, in ionic form both the rings are aromatic, so it's having a 0.8 dipole moment. And what is next, in 2004, what question they have asked, what is the most stable azulene, uh, which contributes the most to the stability of azulene. So this structure is most stable. Okay, then in 2009 what they asked, uh, the the compound this has given. So four options they have given, two, three, four: aromatic and high dipole moment, sorry D, aromatic and no dipole moment, non-aromatic, high dipole moment, anti-aromatic, no dipole moment. So these are the four options. So we know that this is aromatic and having a high dipole moment. And then they have given pyrrole, then thiopine, then pyridine. They ask which one is more reactive towards the electrophile. We know that which one is having more electron density, that will be more reactive. So one, two, three. Pyridine ring is electron deficient. Because of that reason, it's not reactive towards the electrophiles. And this is an interesting question. One, two, three. So the question is, which hydrogen is more acidic among these three? We know that if it loses this hydrogen, it will become aromatic. Here also, this also become aromatic. But compared to these two, third is more aromatic compared to second. So that's why this is more acidic. So here no point of aromatic character, so this should be least. So this is the correct order. Then next question we have, they have given this is option A, option B, C, so they ask which one is a non-aromatic here. So this is very simple. Cyclooctatetrene, it exists in a tub shape. 1 2 3 4 5 6 7 8, it exists in the tub shape. Okay, so this is the non-aromatic in nature. So this is anti, this is aromatic, and this is also aromatic. This we cannot call it as a homoaromatic because this is a these two carbons are connected by a CH2, but this is out of the plane, so this comes under aromatic. Then like A, B, C. So the question is increasing order of heat of hydrogenation. So we know that stability is inversely proportional to heat of hydrogenation. Okay, so here which one is more stable? First we arrange them in aromatic character. So this is aromatic, then this is a comes under anti-aromatic, and this comes under non-aromatic. We can say non-aromatic. Okay, if you see the stability order, aromatic is more stable, then non-aromatic, then anti-aromatic. So stability is inversely proportional to heat of hydrogenation. So C will be having more heat of hydrogenation, then A, at last B. Next we have the one more question here. This is A, sorry, this is B, this is C. No, it's not this. So like this. So we have three options. So if they ask pKa value and acidity, okay, so this one will be more acidic because if it loses this proton, it get a aromatic character. Okay, so we know that acidity is inversely proportional to pKa. So like this also they can frame the question. Then we have OH here, OH. So if the question is which one undergoes oxidation fast, if it undergoes oxidation fast, then it will become like this. If it undergoes oxidation, then it become like this. So here it is a non-aromatic, and it's getting converting into aromatic, sorry, anti-aromatic. Okay, and this is aromatic. Here also this is aromatic only, but uh, if they ask which one is readily undergoes oxidation, so this undergoes oxidation because here it's converting from non-aromatic to anti-aromatic, means stable to unstable. So like this also they can ask question. And then this one, If these two are there, if they ask which one undergoes reduction faster, if it undergoes reduction faster, we'll get a this compound. If it undergoes, we'll get this compound. So reduction faster means this undergoes reduction faster because it's getting converting from anti to non-aromatic. So here it's aromatic only, it's remaining like that only. So this is very important. And there are some examples. This system, this is anti-aromatic. So if we give 2 electrons to this, then it gets converts into like this. So one double bond gets reduced, so that here we'll get a 2CH2. And now if we'll treat with the base, here negative charge, here negative charge, total 10 pi electron system. So initially it's anti-aromatic, and this is non-aromatic, and this is aromatic. Okay. Then anilines, will take anilines. So this is the 1 2 3 4 5 6 7 14 aniline, 14 aniline and 16 aniline, sorry 18 anilines, they are aromatic, and 12 anilines and 16 anilines, they are anti-aromatic. So these aniline systems we can identify, uh, like if you record the NMR for aromatic anilines, so what will happens, the outer protons comes downfield shift and inside protons comes upfield shift. Whereas for anti-aromatic anilines, outside proton will be upfield, inside proton will be downfield. So these points you have to remember. And here this compound is very important. This one. So just count number of pi electrons, 1 1 2 3 4 5 6 7 8. So 16 pi electron system. This is 16 pi electron system, but this is not anti-aromatic, this is aromatic. How? See, if you see the delocalization, this bond, double bond, will not involve in the delocalization. So if this double bond is not involved in delocalization, now how many pi electrons are there? 14 pi electrons. So this comes under aromatic. Even if you treat this one as a, means if you treat this one with the base, like just imagine that this double bond we are reducing, like this. So here also we have a 14 pi electron system. So this is a aromatic. Just all carbons no need to be sp2 hybridization. Okay, here it's a planar and it's involved, its delocalization is there, so it can be exist as a aromatic. And these protons which are present inside the uh, this compound, they comes upfield shift, and outside proton will come downfield shift. So one last question we have here. This is A. This is P. This is C. So among these three, they asked which one is more acidic. So this question asked in 2012 December. So this will be least acidic, because if you see the acidity order also depends upon the ring size. This is more acidic than this. And here we have 5-member ring beta diketone, and here also beta diketone, but beta diketone is attached to the electron donating group, that is a benzene. So B comes at last, and now we need to see which one is more acidic here. So here we have double bond. If you take this one, if you treat with a base, what will happens, it will take one of the proton, this will be O minus and this will be OH, this will be double bond, this comes this way, this goes like this, and this comes like this. And if you take another base, and finally it becomes like this, O, we can write this one like this, O minus, here plus and here plus. Okay, and this is, here also it's aromatic, here also it's aromatic. The only thing is, like we can say that here hydroxy protons are there, they are more acidic. So more acidic will be C, then A, then B. So this beta diketones are very important, so they will ask this kind of question. I have seen many exams, they have asked this kind of questions on beta diketones. And then we have this is called fulvalene. This also exists in this form. This will be plus and this will be minus. This is also aromatic. And what is a homoaromatic? We have, take 8-member ring. If you take this one, this will be homoaromatic. Means homoaromatic means like the delocalization will disturbed by the sp3 carbon atom, that's it.